Okay. Hey, no. Oh, what happened? Okay. Okay. Uh, here, here I never say something important. That means just go over quickly to know that our kernel two kind, single kernel and the micro kernel. Linux has single kernel. It's efficient, but it's not easy to expand, not portable, not flexible, and the modern system like Windows and Mac OS. It's a microkernel. Use the microkernel. So microkernel is the better design for the commercial usage operating system. Module. Oh, okay. Next is modules. So many module operating system like Unix, Linux, Solid, and Windows implement loaded kernel modules. Kernel has a separate core component because separate core component, and when it's necessary, it's loaded into the memories. When not necessary, not included in the memory. So this and additional services are linked as with modules either at the boot time or runtime. So the module is a good design. We not need not anything, everything. So we only need part of that, the module. And our kernel programming is also the module. We build the module, insert the module to the kernel, and after using and I can remove this module from kernel. It's a module design. Okay, you see, each module is loadable as needed within the kernel. Our assignment one has this module, and lab 2 is this kind of module. The module, macOS and iOS, this structures. It's a hybrid system. Application kernel. So the kernel environment. Applications use user experience, application framework, and the core frame, and have different layers. And the user has the user space and the kernel space has different layers. As the application framework may including some database framework, some virtual some of the framework that using this system, different layers. And this is Android. This is important. All of the cell phones, more than half is Android, right? Other is iOS. This Android is still hybrid system, has different layers. This is the user space application. This is kernel space, kernel, and the hardware. And between the user space and kernel space are the lots of layers, like Android framework, like a SQLite is for database. OpenGL is for it's a native language. This is supported by the Android, and some media framework. This is for the Android. This is not a part of the kernel. It's still not application. As application use this kind of this is a system application. All of the other applications use this, like this SQL, this database, like GUI, so OpenGL. Okay. So when you want to do some self-development, you used to learn lots of things. All of this need to get familiar with. Okay, but our operating system course will only discuss the important concepts of that. Okay, that's all. Okay, that's basic things of basic structure of operating system. Okay, and at this time I can be slower because the chapter 3 is going to chapter 3. No, not this. Oh, okay, present. Because chapter 3 is the processes. We're going to the detailed techniques and very important of processes. Every application will run in your computer. In the computer, will firstly loading from a disk. It's stored on disk, loading from a disk to the memory, and run as a process. As I can say, our computer have a, I guess, an example. This one, I know, this one. I can say a computer has maybe thousands of applications. Thousands of applications. Can you see clear? Thousands of processes. That's we need the operating system to manage all of the process. Hey, why is not always work? Oh no, not this.
Welcome to VoiceOver. VoiceOver is description.
Okay, I just simply use this. Okay. That's why I need always use the process. Process is a program in execution. It's not on the disk, it's execution. Like our system have thousands of process. And how our system can manage this? Process execution must be progressed in sequential fashions. So each of the process must run on sequential, and no parallel execution of a single process. This single process like a single person. You can do one work at the same time. You can do both. You cannot do things in parallel. So parallel computing, that means I have two processes can do in parallel. Right? One process is no parallel execution. So process is as that is passive. Program is passive entity. It's loading on disk. But a process is active as active as a loading from the disk as an executable file to the memory. That's a program become a process. The program become process when the executable file is loading to the memory. So execution of a program starting with the GUI, like GUI, mouse click, with the mouse click, command line entry. So one program can have several processes. Consider multiple user executing the same program. So for example, our browser maybe have several processes. One process handle render the interface. Other process that is sending message between the server and the client. That's all. One program maybe have several processes. Okay, here are the important. Here I can be slow. Here's the important concepts of the memory space of one process. So each process can have the from 0 to max. 0 to max. It's a sequential continuous memory space starting from text. Text is the code, the source code, not the source code. It's a compiled program source code. It's loading from the text section. And then the data section is global and static variable. So you declare lots of global and static variables like strings put into the data sections. To put into data section, and the initialize prior to exactly the main. So a lot of them initialized, put into data sections. And the heap is a memory that is dynamically allocated. We will use the malloc. You know, see, use the malloc. It's a malloc the memory from the web heap. It's heap. Heap is grow up. drop. In C++, you use new and delete. Right? In C is malloc free. You manage memory. This memory in the heap. Malloc is malloc memory in the heap. Now, last one is stack. Stack is growth down. Stack is from max to down. Stack is used for local variables and function calls. The stack, this memory is automatically released. You don't need to manually, you don't need to new and delete or malloc or free. It's automatically released. It's a stack. The stack is data structure for what? What's the first out? What's the first out? So if the function call it puts all of the parameters into the stack, and the next time the function finished, will pop out from the stack. That's the first in, first out stack. 1, 2, 3, 4. It's a 4-section stack for a process, and the memory is spacing from 0 to max. What is max here? What is max? That depends on how much memory you have. If it's 32 bits operating system, the max is 4 gigabytes. So the memory space is from 0 to 4 gigabytes. But now we have a 64-bit operating system. So the max can be 16 gigabytes. 16 gigabytes, you see? This is this process can take a whole memory space. Why? Okay, I think this is the hard question. Because for a process, the memory space is from 0 to 4 gigabytes in 32 bits. It can see the all continuous. And every process can see its memory space like this. It's a mapping to, it's need a virtual memory mapping. Like this is a virtual memory space. And for programmer, it's easy. You can see the programmer will allocate the memory from 0 to max. 0 is max to 4 gigabytes. You can allocate the memory easily. You don't worry about, oh, do I have enough memory? Because you only have 16 gigabytes memory in your laptop. Do you have enough memory? Don't worry about it. The operating system will manage this. Even you have thousands of processes, but the operating system gives you this virtual memory space. This virtual memory space, not a physical memory space. It's mapping to the memory, virtual memory. And it gives you illusion that this process has all the memory space, but actually not. Later we can discuss these details. How can we implement this? You see, you only say each of the process has its memory space. Okay. This is important. See, this is a very standard program. Very simple. Right? Very simple. Okay. What's in text? What's in text? What's in text? Okay, so this is his memory mapping. So this program will compile that it's loading to the disk. It's stored in the disk. It's an executable file, right? So this is the memory space. What's in the text?
Code itself?
Yes, the code, the compiled code, not the source code. The binary, the compiled is the binary code. It's put into the text. It's loading into the text. Then what is the data? The data implement separate as two parts. It's initialized data and uninitialized data. So initialized data int y equal to 15. This is a global variable put into the data section. Right here, global variable. There's two global variables put into data sections. And this is y is the initialized data, but the x is uninitialized data. Here, this data section. Here. But why this going to stack? This is a new data. Where is in the values and I going to stack? I think the first time I say that it's very confusing.
Because they're local variables.
Good. Local variable going to stack. Local variable going to stack, and the global variable going to data sections. Why is it going to stack and not going to heap?
So you can get rid of it easy when you're done, or
No, the heap is only for malloc and just the heap. Heap is for you must manually malloc and release. This value is the pointer. This value is the pointer. This pointer point to a memory. This memory is allocated into the heap. Right? The value is a pointer. This pointer is stored in the stack. Okay, confusing? But this value is the pointer pointed to a memory is dynamically malloc in the heap. Heap is dynamically allocated memory space in the heap. But the value is the pointer. This pointer is a local variable put in the stack. So local variable put in stack. So this values and I put into stack because we are doing the function call in the main function call. So after this function call, you see return 0. Oh, the function call finished. So we pop this value and I from the stack. This way can implement this so automatically release. We don't need to release that. But how about this heap? Okay, what happened? I forgot to release the memory. What happened? Here I have my log. This value point to a memory, my log in the heap. But I don't release the memory. What happened? This is the error. Yes, correct. It's the memory leaking. It's memory leaking. This memory is still in the heap, but not released. Memory leaking. But for this program, it doesn't matter because it's a return to 0. Return to 0. This means this process terminate. Terminate the process will release all of the results. This will disappear, and all of this memory will disappear. This is not a correct usage. It's not a correct usage. You should malloc and release. Forgot to release will because some of the application like our browser, you cannot to terminate the process to release the resource. Your browser will quit. Oh, quit, release the resource. So we cannot quit. Your operating system quit. No. Restart. It's not a good method. So this is release the memory by quit. It's not. So this if you forgot to release the memory, this will not release. Probably cause the memory leaking. Because this memory you never recycle. It's a total waste. Okay. How about array like int a 100? Because here I initialize a pointer and point to a memory address in the heap. How about I initialize the array like this? Where is it located? This. I think this is the most important in this course. You know the details of, we'll write this code. In your mind, you know the memory structure of this code. How about A, initialize the array like A100? Where is located? Where? I must say it's in the middle of final design. Where is located?
does it depend on where it is in the program?
Yes.
It's in the choice.
Yeah, where?
Does it depend where it is on the program?
No.
Is it the uninitialized data?
No, it's okay. It's on the stack. Because it's a parameter. It's an array. It's a parameter. It's in the stack. The stack can allocate this memory space for A.
How about like, so right now you write down the very top int x. But if you.
Oh, if you use the
A,
Oh, good, good. If you write in the top, it's global variables. So it should be going to the uninitialized data. It's good. Great. Uninitialized data. So this will going to here. And if you write this array to here, this will allocate to the stack. Allocate the stack. Good part, you know that. Because this is a local variable. Local variable is a array. Array will allocate memory from the stack. The A100 is from the stack. And this is not a good method because the stack is always very small. You allocate a very large memory in the stack, like A100 is an array. Stack is very small. You see, the stack is always used in the function call. So the local variable, you allocate such a large array in the stack. That is too dangerous. What happens if the stack overflow? We also say stack overflow. This is stack overflow. Okay, well, for example, you can allocate the array has a millions of sites. It's easy to cause a stack overflow. And remember, the Python, the stack maybe different machine have different stack size. 1 megabytes, maybe. You can use the command line to ask your system how the system supports how much the stack size, because the stack size is limited, but the heap size is really large. Like you can how much of your memory, like 16 gigabytes, your heap size can reach up to 15 gigabytes. Heap is good. So this is a good writing method. It's a good style writing. And allocate the array like this is not good. You take the stack. Also, this here. Also here is the data. You see data. This is small size. This is small size. Allocate the memory like outside here is array here. It's going to the uninitialized data. This is still dangerous. The data size is small. Okay, so remember, when you want a large memory, malloc on the heap. Malloc on the heap. The heap can be very large. How about the function call of malloc? When you do the function call of malloc, what happened? Firstly, it will the malloc has a parameter of size of int 5. This is size of int is 4, right? Last 5 is 20. 20 is the parameter. This parameter will stored in the stack. Like I said, this is the function call. It's a function call. Function call. This parameter will store in the stack. Good. The function call. The file will store in the stack. Function calls the stack, and all of the this and this will store in the main, because we go to this function, and this main and this variable is also stored in the stack. And after this function call finish, malloc finish, it will return to the main function and it will return. So the stack will pop out this all the things in the malloc and return to the main function. Good. Okay, what happens inside the malloc? Malloc will trigger a system call. Because all this is running on the user space, user module. And the malloc's memory is must happen in the kernel mode. It's a trigger a system call, tell the kernel that can we allocate this memory in the heap. The kernel will malloc the memory and return the address of the value. This value will point to a memory address in the heap. And also this the kernel will maintain this will remember also maintain this table to what's for this malloc. And this malloc must be paired to the free. I not show the free here. If you this value, this address is not matched to the free, which causes error. Okay, this value is point to the malloc memory, and if you change it, because move this value is the pointer increased by 1, so the pointer is not the original pointer. If you release, this will cause error. Okay, you can try. Okay. Okay, lots of third question. Is heap memory released or not released? We just not released, or does it have the memory leaking or no? Yes, it has memory leaking. We just discussed. Last question is what happened if what happens? This is correct. This is correct. This one.
Yeah, just guys, so for the third question, the question before says, so how do we actually close that? Do we have to say release values or delete values or?
No, the malloc release this value. Release the value, it will release this value. Okay, last time I will write here. Malloc has released not used by here. Malloc this memory as released from this pointer. This pointer then going to the kernel, use a system call that will because use this pointer to find out, oh, this is the malloc memory for this pointer. The kernel system call will manage this. The kernel knows how much size it is. How much size it is. That's okay. Next time I ask this release. Good question. Good question. Here has lots of details. So we discuss the back. What happened in the background has lots of details. Okay. What happened? This. It will cause
It will cause an error because you're only initializing 5 positions, depending on the value, then you're giving it 6,
yes.
0 to 5.
Yes, because the memory size is 5. From 5 is the value is array. The array like from 0 to 4. But 5 is out of the bound. Out of bound. So here you access the value that is not in this allocated memory. So this will cause okay, if you mark the memory here, that will cause the next access will go to here. But this memory is not allocated. And good thing is the C compiler will never tell you this is the error. And when you run it, we not error, it will never tell you it's an error. That's why the programming in C is difficult. In C, programming compile is good, no errors. Running is good, no errors. This value will return a random or arbitrary value because maybe it's 0 because it's not used. Maybe it's the other value. Unpredictable. Nobody knows what it is. Maybe when you're testing this, maybe this time it will return 0. Maybe you test the next time it will return 5. Nobody knows. And the compiler will run the never tell you it's error because C don't have this boundary check. See, it's a memory as an array. It has boundary. It has boundary from 0 to 4. And C don't have a boundary check. And lots of bugs happen like this. And when testing, okay, testing is good, but next time wrong is wrong. So I say it's unpredictable. This is unpredictable. How can we solve this? No, in C we cannot solve this. We have lots of tools to check these boundaries. It's not C. It's not a compiler. It's a programming tools to check these boundaries. And otherwise you can use Rust. Rust can run this boundary check in the compile time. C designed like this without the boundary checking because C one is more efficient, running faster. Boundary check is always slow because like I say, every time you run here, you check the boundary. It's the waste of running time, waste of CPU resource. So C don't have this boundary check. It's very dangerous here. when you have millions lines of code, how can you detect this? It's hard. But this has a lot of details. Okay. Let's go on. Here I can become slow. Okay. Oh. Okay. Buffer overflow. It's called the buffer overflow. Okay. Process state. Process state. As the process executes, it changes the state. With this, we're going to the details of a process. We have 5 states. Okay, new, running, waiting, ready, and terminating. I think it's better to explain in this diagram. So when you start a process, what happened? Okay, new. We create a new process. This process will go into the ready. Ready means this process, okay, should run, but the resource is limited. We have thousands of processes going to ready. Ready when you when the schedule dispatch, we use the scheduler give this process resource, or we schedule tell this process each time to run. It's from ready to running. This is because say thousands of processes on the CPU is managed by the scheduler. This scheduler will schedule all of this process. Or if you are ready, but we don't have resource, you just wait. On next round, we have resource, the allocated resource will become running. And the running, when you're running, it is possible by an interrupt. Here, interrupt. And going to ready. What is the interrupt? What is the interrupt? Interrupt. We discussed in the first class. Yeah.
A signal from a hardware device.
Yes, it's a signal from hardware device. It's not. It's to solve the problem for easy checking. Running. For example, when a process run, it need a file read or file write. You read the file. Read the file that's we don't need CPU, and need to cause an interrupt. CPU will not always busy checking, oh, do you need to read the file? No. And the program will trigger interrupt. They'll tell, oh, that's from running to ready because it's read the file. Writing file is very slow. The disk is slow. CPU is fast. Why we must let the CPU wait, stupidly wait? So we simply put this process from running to the ready. Okay, so the scheduler dispatch can schedule other process to running. Good. The ready to running. Then from ready to running, that's scheduler. And from running to ready is the interrupt. Okay, so from this pattern. And after it's finished task, this process can terminate. Terminate. This is easy. Okay. But then here, the running can go into the waiting. Running can go into the waiting like the IO event or with some wait. So your running can be the waiting. So it's removed from this random as it become waiting. And this waiting is waiting. And then it's going to IO event complete. Oh, it's an IO event because this process will do in other things. But maybe it can have some send a message to server, like a network, use a mesh network, maybe as a IO read or write. Some IO maybe waiting for your type some command lines, type a username and password, and going to waiting. And then after that one going to the ready. Waiting is waiting must be have some scheduler put into the ready. So this is process state. Process state. Okay, this is you need to know this is a 5 state. Okay, go to here. This is I know it's very abstractive. Later we can show some examples. Okay. This is PCB, the process control block. This is the implementation in the kernel mode. And each of the process have the PCB, process control block, to record all of the status. It's active, it's running. It's the status is if this is ready or running. So it's the process state, there's the process number, process counter, registers, memory limits, list of the open files. It's record the list of the open files. Yeah.
Sorry, just a question about the last slide, when you were talking about when a process was ready and then, like, for the example of read write file, wouldn't that go down to waiting instead? And then because it's waiting for.
Oh, sorry, I may make a mistake. So the IO event will go into the waiting. This will go into the interrupt by some interrupt.
So let's say there was some kind of like an interrupt, is an interrupt like something critical, like something is wrong, let's say. The clock is, the hardware is not available because of something else. Or another process of a higher priority that needs to get balanced.
Interrupt is not an error. Interrupt is not an error. Interrupt will have lots of some software interrupt. Like system call is kind of an interrupt. System call is the interrupt. It's from running to the ready. Because and some error may be allocated memory. The memory is not enough. It's also kind of interrupt. Also kind of interrupt. This it's including lots of details. We will discuss later. We just going to because it's a really huge topic. We're just going to give you a big picture. And the next time, add more details in the one part. And next time, add more detail in this part. And after you finish the course, you should go back to review that, and you have a different view. Okay, because this diagram includes, I cannot discuss too much. This interrupt including software interrupt, like what is the memory? So how about this? Don't have virtual memory. How about this? I don't have enough memory. It's called interrupt. Or cause on track. It's a form running to ready. Okay, waiting for this allocated enough memory. And here's the IO, because IO is much more slower than interrupt. Waiting for you input your username like password. At least 5 seconds passed. So if putting to ready is not a good idea. It should put into waiting. Put into waiting. Here, okay. If you check the textbook that has more details. Okay, and later we'll have discuss more. Okay, back to here. That's the implementation PCB. You can see the source code from this 15. Okay. Okay, this is for today's class. Next time, if I take some more time, then let me know. Okay. So next time we going to this Canadian part.
We absolutely.
One more thought. Sorry if you could ask the question. But about the slides, I made a copy of all the slides from before, so I'm going through them, but these slides again, not on the website.
Yeah, I always post on this line. I sent it yesterday.
Okay, thank you. So it will be paid well later.
You can click those slides, that's how I log this slide.
Thank you so much.
Any questions?
It's still very, like, it takes a while to get out.